We're going to concentrate today on 2D sketching. And if everything goes according to plan, we're going to spend more time practicing what things we should go home and practice before the next lecture. So it is supposed to be a practical class where hands-on, you will see me demonstrate what I want you to do. And as you gain those skills, you will, by next week, I'll give you the assignments that is pertaining to the first 4 lectures. I will do that by next week. And please note, I should mention this in class now. Please note that students can make contact with me now, especially when they have questions to ask. That is why I give email address and even WhatsApp number, but they're available to you. If you don't use it to ask me any question during the term, and you are using it to harass me for your grades at the end of the day, I will just not answer you. So I will just ignore you completely. The reason why I gave you my number is to help you during the term. If you think you can use that to eke out marks out of me, you are making a big mistake. I'm not going to answer you. But if you have been discussing with me during the term and you have a problem, of course I will listen to you and I will respond to you. But if you think the only thing you can do with my contact is to be asking for marks, you are making a mistake, because I am here to teach you. I'm here to help you. I'm not here to just be dashing you marks. Marks are the least of my problems. My problem is, do you have the skills? Do you understand this? And can you be productive using these things? Those are the things that bother me, not the issue of can I get marks? So today we are going to concentrate on 2-dimensional sketching, but to make the class more holistic, I'm going to go through a review of things we've touched on before you went on your election break. So the topic is 2-dimensional sketching, but we are going to talk beyond that, initially at least. The complete assembly. It is a good idea to be mindful of the ultimate goal of your design prior to attempting the underlying 2-dimensional sketches needed to create it. So you have your design. Your design will have some 2-dimensional sketches that you need to be able to create it. Even though the design is in 3 dimensions, there are certain fundamental 2D sketches that will be needed to be able to properly create the design. So, but you have to have in your mind what the ultimate goal is, and that is what will drive you to do your sketches correctly and to know the kinds of things to do. We shall use this process to instruct on basic sketching ideas. We are going to do very, very simple sketches, and you will see how a very simple sketch can create very important and non-trivial 3-dimensional models. So that is what we are going to achieve into this class. We will use this process to instruct on the basic sketching ideas and move stepwise to the final design. We shall also learn the fundamentals of component-wise design that will be useful in the final assembly process. It will also be useful in the simulation for strength, for prototyping, and parts manufacture to the final product. What we are doing is actually how to make things. We are not just drawing for drawing's sake. The drawing is an initial step into manufacturing. So what you are really learning is manufacturing, but we are starting with a physical rendering, a computer rendering of what you are going to produce eventually. So you always have to bear the complete assembly in mind before you even do anything. In order to do this, there are abstract entities and containers that you need to take care of, because Fusion 360, just like a standard 3D solid modeling package, is organized around some abstract entities which we call containers. To succeed in solid modeling, it is important to understand the principles that govern the way 3D solid modeling arranges elements of a design. Elements of a design are arranged in a very logical way. So if you understand the logic, you will find out that your ability to create the graphics will be greatly enhanced. If you are just doing trial and error, especially if you go to the web and you are just taking incompetent people that just did some tickling around to know it, you will do something, but you will achieve better results if you understand the principle behind it. The arrangement itself follows a set of rules that are tightly maintained. You will encounter many terms such as joints. They mean specific things. Bodies mean specific things, and components also mean specific things. What do these things mean? In today's lecture, you ought to understand the meaning of these terms. They may be close to the ones you are used to in the ordinary usage of the word, which I call the doppelgangers, but their own meanings are a little bit more abstract and may be wider than the concrete examples. A good example is, what is a body? What do you think a body really is? What do you think a component really is? And what's a joint? You'll be surprised when you really fully realize the meaning that Vision 360 gives to joints. You will see things that you will not even think are joints, but they're actually joints. Basic elements. Drawing elements in your design start from primitive entities in your sketches, such as points, lines, curves, and combinations of these. Other design elements include construction lines or points or planes that aid the drawing. Those construction lines are not part of the drawing, they are just aiding the drawing. And because of that, we will distinguish between construction lines and ordinary lines. You will see that construction lines are displayed in dashes, whereas the real lines are in continuous line objects. Similarly, you will see that we use continuous lines to do dimensions, but those are slightly thinner than the ordinary lines for you to separate them. You should be able to know which one is a construction line, which one is a dimension line, and which one is a real line that is part of your design. It will be important for you to distinguish between all those. Joints that orchestrate this static bindings and motions, named views, and design wide settings that hold things like default units of measurement that you set. There are other design elements like that. So you have basic design elements like the primitive entities. You also have other things. And we have explained it now. What joints do is that they orchestrate displacements. They also orchestrate static bindings. And then they orchestrate motions, named view, and design wide settings that hold things like default units of measurement that you can set. Top level component. So every design has a top level component. There's a top level component. Everything you do in Vision 360, you are essentially doing it in a component. And the top level component exists by default. And it bears the name of the file under which your design is stored. By the time you name your file, that name is also the name borne by the top level component. So your top level component has the same name as your file. Now, a top level component or any component is an abstract container that includes document-wide. So the top level component is an abstract container that includes document-wide objects, such as document settings and named views. The named views give you an easy access to basic projections and a way to look at a way back to your home screen. The basic projections are just different viewpoints. For instance, you might look, if you look from above, We call that the plan. Then we look from one side, the side elevation, and then from the perpendicular side, another side elevation. So you can look at that as X, Y, Z directions of view. So those are named views. The named views give you those projections. So you can quickly go there. But that's not the only way you can go to those projections. There are other ways. There is the view cube. We discussed the view cube in the last lecture. There's a view cube that can also take you to the same places. But the named views will always be available on your browser, and they will take you to those basic projections, and there will be one of the buttons there that can take you all the way back to the home screen. In addition to this, components contain the following, in addition to what I have described. The components can contain the origin. In Fusion 360, when we say origin, we actually are referring to the coordinate system of reference for locating all objects in the component. Each component has that coordinate reference. The coordinate reference is always existing inside the component package. And then in addition to the reference, you have coordinate lines. You have also the coordinate plane. So if you want to move, you know whether you are moving along x-axis, whether you are moving along y-axis or along z-axis, or whether you are walking on the xy plane, yz plane, or the zx plane. So it is always from your origin, which is the coordinate system, you can always get where you are going or where you are walking. And you can choose. For instance, if you need a plane, you can go to the origin to select any of the coordinate planes. You may be able to select other planes from other methods, but those are always available inside your component. Once your component is defined, there are at least 3 planes that you have available to you in case you need to perform a function that requires a plane. One such function is to sketch. If you want to sketch, Fusion 360 will prompt you to supply a plane. You want to sketch, okay, it's just like you tell me to sketch something. I say, please, can I have a piece of paper? So when you say create a sketch, the first thing Fusion 360 will do is, okay, you want to create a sketch on what plane? You can create your sketch on the XY plane, or the YZ plane, or on the ZX plane, or on a plane that you define. So we'll see later how you can define a plane yourself. So you don't have to use the coordinate planes, but what we are saying here is that the coordinate planes are always available in the abstract called origin. So when you see origin, it doesn't just mean origin. It is the coordinate system of reference for locating all objects in the component. And they include coordinate lines, coordinate planes, as well as an origin. Second, analysis. Your component can store, apart from the origin, it can also store analysis. For instance, you might do a section analysis. You might have a 3D object, and you want to say, okay, suppose I take a slice. Suppose I slice through this object. How will the section look like? You can take any slice through any section in any direction you want, and you will see how to do that. When you finish, such analysis do not disappear. Such analyses are stored under the analysis section of your component so that you can refer to it over and over again. Unless you cancel it, those analyses are actually stored inside the analysis section of your component. 3, joints is an abstraction that expands the concrete idea of physical joints to include entities that orchestrate joining, fixing, displacements, and motions that are possible among components. Please be very careful. Joints only join components. They don't join bodies. In the next few slides, we are going to distinguish between what is a component and what is a body. So if you just have a group of bodies, you cannot have a joint that is connecting them. It's only when you have a number of components that you can now have pairwise joints that are joining the components, and those joints orchestrate joining. They also orchestrate fixing. What do I mean by fixing? Suppose two particular components are to be tightly bound together, that they should not have any relative motion. So what you do is that there's a joint between them, and you will say that that is a fixed joint. That fixed joint guarantees that there will be no relative motion between them. If there's going to be a motion, then you have to know, is the motion going to be a rotatory kind of motion, like a revolving thing? Is it going to be a sliding thing? And so on. So the joint, again, will have that characteristic, depending on what kind of motion you want to make possible between those two components. So the joints orchestrate joining, fixing, displacements, and motions that are possible between two components and therefore among components. Number 4, inside your components, you can have sketches, which we will say much more about shortly. Sketches is a combination of drawing entities such as points, lines, and curves that form the base of your design and other finishing parts. So you can have several sketches in a single component. So if you have several sketches, they will be in the sketches section, and there can be more than one sketch there. Construction points, lines and planes that catalyze the drawing process. In addition to those are construction points. In addition to this, components can contain other components and bodies. So, but the top level component is defined for you. And if you create a body and you do not put it inside one of your own defined components, it will remain inside the top level component. The other components you create are part and parcel of the top level component, but they can on their own contain bodies. Joints and timelines. A joint entity, for emphasis, is only possible in the top level component or in components that contain other components. And let me explain what we are saying here. If all your components are simple components, that is, they do not on their own or contain other subcomponents, that means that all your joints will be present only in the top level component, because a joint can only create relationship between components. So a multi-body component, for instance, a component that has several bodies, will contain no joints, whereas a multi-component component will have joints. If that looks a bit confusing, let me explain. It is possible for a component to have other components, and these things are too abstract. So we will show with specific examples that you will see and you can create for you to understand. So do not try to memorize anything. All these things are going to come in shortly while we just go through the practice. Joints are related to what, if you still don't understand it at that point, please ask your question. Joints are related to what is understood by the ordinary meaning of the word, but it has a larger meaning in solid modeling. In a timeline-oriented modeling tool such as Vision 360, each component is imbued with its own timeline. These timelines are like a set of slides that show the creation history of that component. So you can actually play back these slides and to show you how the component was created up to the present state of the component, from the beginning of the creation to where you are presently at. So that timeline can be played back, and it is the creation story of the component, and you can observe it by that play. You can also scroll through it as the artwork on your own pace. You can play it back automatically, or you can also click one by one and move through. And you can also order of creation manually. So you can use your hand to actually rearrange the order of creation. And there are so many things you can do. There may be reasons for doing that, which you will see as we move on. Bodies. We have, bodies. A body is a connected three-dimensional region. A body is a connected three-dimensional region. I assume you know what a three-dimensional region is. For instance, where you are watching this video from is a three-dimensional region. It could be your room, it could be your classroom, it could be your bedroom, it could be your study room, it could be your living room. It's a three-dimensional figure because you can always have X, Y, Z axis and you can locate points in it. Now, if you have a particular region defined, for instance, region occupied by a piece of an entity, that region is connected. If any two points can be connected, can be joined by a simple curve that lies wholly within the region without getting out of the region. Now, if any 2 points can be connected within the region, then that region is connected. If any 2 points, any two of its points can be joined by a simple curve that lies wholly within the region, it is connected. If an existing body is disconnected by either by a surface or another object, new bodies result as each defined body must be connected. The body section in any component can contain several of these connected entities. All these are part of the makeup of the component. In order to be sure you are awake and you are hearing me and you are thinking, I want to ask you, is a donut a connected region? I want somebody to ask, see the definition of region here. I want you to go to the chat room and respond to me and tell me if a donut is connected, is a connected region. Is a donut a connected region? Okay. Is a solid sphere. Is a solid sphere a connected region? Is a solid sphere a connected region? Okay. Okay, so a donut is a connected region, a solid sphere is a connected region. Most of your bodies are connected. Okay, suppose we take a bite of a donut. We take a bite out of it so that the hole becomes open. Is it still connected? If we take a bite of the donut so that we open to the middle hole. Okay, on what you say is no longer connected. Oluwatolamishi says it's no longer connected. Unfortunately, you are wrong. It is still connected. It is still connected because, you see, remember, the definition of connectedness is that you can take a simple curve. You can, apart from the part you have eaten, you have, Udo, you are right. If we are still talking about the one that is already inside your stomach, no, I think that one is gone. I'm just talking of what is left. Udo, you are right. So I'm talking of what is left. What is left is still connected. Okay. Maybe I should just take a diversion here and say, in the case, there is a difference between the way a donut is connected and a sphere is connected. A sphere is an example of a simply connected region. Whereas a donut is a multiply connected region, but both regions are connected. We have another definition for simply connected and multiply connected, but they are not relevant for our work here because we do not care whether the region is simply connected or multiply connected insofar as the region is connected. But let me just leave it to you because we encounter this in your math at 300 level if I teach it, or it's already in the syllabus. So no matter who teaches it, it should be. The definition of a simply connected region is that if a closed curve, if any closed curve can be shrunk to zero, to a point, without leaving the region, then the region is simply connected. If that cannot happen, then the region is multiply connected. So, but to be connected is at any 2 points is connected, can be joined by a curve. To be simply connected is that any closed curve in the region can be shrunk to a point without leaving the region. So in that case, what kind of connection do we have in a sphere? Is it simple or multiple for a sphere? Is a sphere simply connected or multiply connected? Okay, a sphere is simply connected. What about a donut? What about a donut? Is a donut, okay, a donut is multiply connected, but both sphere and donut are connected. So we see, good class, the class is alive and awake. So a body is a 3D region that is connected. And it is connected if any 2 points can be joined by a simple curve that lies wholly within the region. So when we have something like that, we call that thing a body. And the body, whenever anything you are doing is simply connected, we can call it a body. If we slice it into two so that you can no longer join, then you now have two bodies, because each body must be simply connected. Each body must be connected. If you can slice it into two, if you cut your donut into two, you are sharing it with your friend, then the one that you have is a body. The one that he has is another body. Even though they originated from the single donut, in Fusion 360, we will no longer consider them from that point. When you have sliced them, we will no longer consider them a body. They are now two different bodies. So it is important for you to know. We have explained what we mean by a component. We have now explained what we mean by bodies. The body section in any component can contain several of these connected entities. All these are part of the makeup of the component. Now, we want to talk about faces. Faces. Faces actually are the surfaces of bodies. So a single body can have several faces. For instance, a cylinder can have a curved surface, and a solid cylinder can have a curved surface. That's a curved face. And it can have two faces that are planar. So you can see a single body can have three faces. So bodies are bound by surfaces that are called by their abstract name faces. In Fusion 360, we don't talk of surfaces, we just talk of faces. Bodies may be simple primitives such as cylinders, cuboids, or spheres. They may be complicated entities, combine these and many other things. Bodies may be created directly using 3D tools. There are 3D tools that create bodies straight away. They can also be created from 2D sketches via operations such as revolve, we will see that, extrude, loft, sweep, and etc. There are ways you can turn a 2D sketch into a body using extrusion, revolution, lofting, or sweep. Each body in your design is necessarily associated with a component. It's either associated with the top level component, that is the default. If a body is not located inside one of your created components, it is necessarily accommodated in the top level component. So there is no body that is just hanging. A body must be held in a particular container. So it must belong to a particular component. We are going to use a concrete example of my drawer cabinet, which I introduced in the previous lecture. We are going to look at it a little bit more closely, and we'll use it to motivate some of the definitions that we are struggling with here. Now, it is not a problem for us to go straight and draw some engineering body like a turbine, a compressor, a heater, a car brake, or something like that. But I want to keep it very simple to everyday objects that you deal with. Let us just initially keep it very simple. When we keep it very simple, we are going to understand those concepts in the simplest ways, so that there's no doubt about what we are achieving, what we are doing, what we are talking about. You are not under any illusion as to what we are discussing. So that's what I want to do. I want us to discuss the simple drawer cabinet. More specifically, we will initially focus on the slider mechanism that enhances the motion of drawers in the cabinet. But we are going to take one component after the other, create a 3D thing, and assemble them together and create a cabinet that actually works abstractly, that we can see in our computer, and we can open the cabinet, we can close the cabinet, we can do all sorts of things. We can activate the joints and see that all the possible motions and possible fixings are obeyed. And this component is also a container for other components. When we pass from external sources, the component we will call the slider mechanism is a component of components. We will take a look at that and to spend time gaining valuable experience by taking a look at that particular example. This component is a container for other components, and several ideas in joint assembly, constrained motion specification, connected and disconnected replication, etc., will be taught in concrete terms to give you the skill necessary to do these things in more complex settings. After we have taught this in concrete terms, we'll go back to theory again, because once you understand what we are talking about, it is easy to base more theory on the concrete example that you are very familiar with, that you can actually create on your own. You can work on it and you can produce it. Once you can produce it using the tools in Fusion 360 and you have gained some expertise, then I will be ready to talk more theory. But not until then. The first thing in my mind is to make sure that every time you have a lecture, you spend at least 2 to 5 hours playing around, fiddling around, and improving your skill set. Because the whole idea here is that you become a skilled engineer that can actually not just cram and produce what I've said, but can turn it to skill that you have. And therefore, you can be productive and you can be employable and you can actually do things for yourself. This picture here I showed you before, this is a photograph of my drawer cabinet. And I want us to look at this drawer cabinet, and we will pause a little bit here. In this example, we begin with something that exists physically. That this is a special case. In your designs, you may be dealing with an idea that exists only in your mind, and a rough hand sketch may be necessary. But let us try and start with this thing that actually exists. And this is my study lamp on top of it. Okay, so the study lamp has LED, a linear set of LED lights that you can rotate. You can rotate that and turn it to any direction you like. In the assignment for the next 3 weeks, you will use a piece of furniture or another artifact that contains moving parts. Then you can measure dimensions and implement the model directly. What I'm saying is that when you are doing your own, the one you will submit for your homework, it doesn't have to be my own filing cabinet. You can take any other filing cabinet, any other drawer cabinet that you have in your house or in your room or in your classroom. But what is important is that it must be such that there are doors, there are openings, there are relationships of motion or displacement, because we are going to also want to discuss assemblies and joints. Before we go on, can somebody, I want to challenge the class. Please tell me the different components you think we can create from this picture. Go to the filing cabinet, go to the, and let me know what you really think before I now start. What can you see in this place? If out, I will supply it. What do you see present here? give examples of components that you can see here. Okay, somebody says the cabinet handle. Good, that's a component. So you'll see that in the cabinet handle, we will make 1, 2, 3, 4, 5, 6, 7, 8, 8 or 9 of that. Okay, good. Oluwatolamishi has responded. Is it that you don't understand my question? Look at the picture. Okay, the drawer, that is ambiguous because there are two types of drawer. There is a large drawer and there's a small drawer. They are not the same. So you can say large drawer and small drawer. Okay, what else? Okay, so a large drawer is a component, a small drawer is another component. What else? A keyhole, or okay, just the key system. Well, good. What else? A doorknob, good. Door handle, good. What about the door itself? No, the movable internal drawer, the whole drawer that is moving is the same, is a whole component on its own. The large one, the small one. Yes. It's a component by itself. Okay. Okay. Good. The class is alive and I'm happy, so we'll move on. Now, this is my 3D solid model of that same drawer. So this is a drawing in 3D of that same drawing. So can you see more stuff now? Can you see, for instance, the slider that holds the drawer, the filing that holds the drawer to the body of the drawer cabinet itself? Can you see that? Like this one here. We pull this one completely out. We didn't completely out in the other ones, but pull it completely out for you to see here. Okay, so you can see this. So there is more. You can see immediately the things you can do with a 3D solid model. So there are so many things that are possible when you are put it in 3D solid model. Okay, let us see what comes next here. Now, this is the same, this slider that you are seeing here. This is a slider drawn by itself. The slider contains 3 components. It contains the outer slide, middle slide, and inner slide. There are 3 components. Each one contains bodies, but contains more than bodies. So that I don't dictate to you. Can you tell me, for instance, this inner slide that is in the center here, what else does it have apart from the body of the, apart from its body, the main body? I want you to tell me, what else is there? What else does this contain? Can you see my arrow, my mouse pointer? Can you see my mouse pointer? Okay. Oluwatolamishi says it has 4 holes. That's good. And in those holes, what can we do with those holes? What can we do with them? Oyi Consola Fashina, what can we do with those holes? Yes, we put screws that actually join. You see, the holes on the inner one joins to the drawer. The holes on the outside joins to the body of the filing cabinet, and that's how the motion between the two will now be enhanced. Okay, you can see that. So you can see that this thing has the body, it can also have holes, and it can also have screws. So the body, the holes, and the screws together constitute the component inside. The component in the middle contains only the body and the holes. And can somebody tell me what purpose the holes of the middle component will perform? Can you tell me what function will they perform? Consola, usually we use screws, but nails, especially crude carpenters in Nigeria, will use nails, but they are supposed to be screws that will join those things because nails can easily be removed. The holes hold the outer and inner slide. No, the outer and inner slide are held in place by the grooves, and the grooves are there, not the holes. The holes can allow you to put your screwdrivers through those holes into the one that is inside. So the holes in the blue middle section should be relatively larger than the holes in either side, so that without completely opening, you can still reach the screws inside. So that's what you can do with that. Ensure this. Okay, I've explained. Samuel, I hope you understand now. Samuel Kwelu. Do you understand now? Samuel? I want Samuel to answer me. Yes, okay, good. Good, Samuel. Okay, so you can see here, we know there are many, components here. But in today's lecture, we're going to concentrate just on the slider. We're going to concentrate on the slider, and we would do enough to be able to make that slider remaining the holes. Those holes can be done easily later on, but we will get that far. We'll get almost as far as the holes today. Let's move on. Before we start our sketches, let me make a point on symmetries. It's a good idea to observe intrinsic symmetries, if any, of the objects before you sketch them. Doing so, we usually have your label for each line of symmetry. So if you have one line of symmetry, you have half of the label. If you have two lines of symmetry, you have 1/4 of the label. So it's a good idea to check if there are symmetries in your work, and so that you do not just do unnecessary work. Not only so, you will do less work, and this is more efficient, and you produce more accurate drawings, more accurate designs, if you take care of the symmetries. Okay, so let us now, we are now going to start on our journey to create the slider. We're going to start on our journey to create the slider, and I have given here half of the cross section. It is half of the cross section you are seeing here. You are seeing it in the isometric view. So later on, we look directly at it. So we will create the basic drawing. Then after we created the basic drawing, we're going to fillet and enhance it in other ways. We're going to create fillets. If you don't know what fillets are, you will learn what fillets are. And then there will be other enhancements like we are going to make double lines instead of single lines, and you'll see the tools that we use to do that. And then we are going to create what will become the groove and some other things to make it do the work we want to do. After that, because we are drawing only half, we are going to use a mirror facility to now produce the other half. But we will not do that until we are finished with, once we are finished completely with one side, then we will do a mirror. And then after we have done the mirror, we will just go through a quick extrusion, creating bodies and components. And then later on, we will come back to it later on and do assembly. And then I will give you an idea of how to now use all of this to do simulation. So there are so many things we will do, but these are the steps we will take to get this slider done. This is a very simple thing, just consisting of lines. This is the same thing now in direct view, but this can be a little bit confusing because it has all the dimensions that you may need on them. So in order to create the basic slider sketch, begin with half of the cross-section of the slider. There are several ways to get this done. So let me see whether I can do the first leg of the drawing before we go on break. In order to do that, let me bring up my Vision 360 page. To do that, Vision 360 page. Okay, so can you still see let me turn this off. Can you see my Vision 360 screen? Can you see my Vision 360 screen? Class? Onwarding. You are answering yes to the, okay, so 2 people have said they can see it. So let me move on. So what we are going to do is that we are going to start here and we are going to say, create a sketch. So you go here, create, and then immediately you have this drop-down menu and you choose create sketch. Once you choose create sketch, you are prompted to decide on what surface, what plane that's lying on. It doesn't matter really which one you choose, but I deliberately choose the YZ plane. And once you choose the YZ plane, you can see that you are looking at the plane directly. If you don't like it that way, you can use you also have a sketch palette on your right-hand side. If you can choose not to look at it straight and go back to the isometric view by pressing home. So you can come back again and say, look, you can toggle between looking at it straight or isometric view. Or you might even go to the preferences. If you go to the preferences and click on your, if you go up and click on your, and then you select preferences. If you select preferences, under those preferences, you will see that there is under the design, on the left set of tabs, you see one called design. If you see design, you will see that 1, 2, 3, 4, 5, 6. The sixth toggle there, say auto look at sketch. The auto look at sketch for me is on. That is why anytime I decide on the plane now becomes a direct look, because there is an automatic change into automatically looking at the plane of sketch. If you turn that off, that feature will be disabled. But you can always go to look at under your sketch palette. So it doesn't matter whether you are automatically looking at it. You can use the look at under the second issue on your sketch palette will allow you to do it. So let us try and do the drawing. To do the drawing, you will see that the first set of tools, 1, 2, 3, 4, 5, 6, unless you have changed it, the first 6 tools are creation tools. One of them is line, the other one is spline, another one is circle, then is mirror, dimension, and rectangle. You could also bring down the create, drop down. That one gives you many more things that you can do there. So the ones you see on top here are just the common ones. And then the next set of 3, they are to help you modify. That you have fillet, cut, and offset. But if you bring it down, you have many more things that you could do there. And then the next set of tools you have are constraints. There are constraints. Those constraints are plenty. You have the horizontal vertical constraint. You have the coincident constraint, the tangent constraint, the equal constraint, the parallel constraint, the perpendicular constraint, fix on fix, midpoint, concentric, collinear, symmetry, and curvature. All those things are, so when you create a drawing, what you are doing is that you are creating something, modifying and constraining it. So instead of using too many words, let us try and draw what I showed you before. And I will do that by just picking a line. And without further ado, I pick the line. It doesn't matter really. I just draw something that it looks closely like what I'm looking for. It doesn't matter whether it is exactly what I'm looking for or not. And you will see very soon the reason why. It doesn't matter too much. Okay, so if I'm happy with the first set of lines that I've drawn, I click OK. You will see that I've done this. What I'm going to do now is that I'm going to put some dimensions to make it exactly what I want. Those dimensions are on one of the slides I gave you. So I will just say create dimension. So the dimension, I want the distance between these 2 points to be 5.5. My own units are in millimeters, 5.5. I want the horizontal distance here to be 7. 7. I want the vertical distance here to be, the vertical distance there, I'm using 3. And I'll move it away here. And then it has canceled. It has created some problem here. So the problem is that I want these 2 points to be at the same, on the same line, on the same vertical line as the original. So what I'm going to do, I would have to use constraint because I don't like this bending that I've seen here. So I'm going to choose horizontal, vertical, and I'm going to choose these 2. So I forced those 2 to be on the same vertical line. And I also want them to be on the same vertical line as the fixed origin. So these 3 points, 1, 2, 3, are at the same vertical line. So there is no problem there. Now, the next thing I want to do, I want to pick the line again and start from a point here. Let me start from pick the line tool again and start from here. If I'm not able to get it right, there's no need to worry about that because we can adjust and finish using the constraints. Okay, so that is done. Now, let me show you this. This particular one, I want it to be aligned vertically with these other ones. It's easy to do. All I will just say is that I will just choose horizontal, vertical. I pick this one, and I pick this one. So it is horizontal, vertical. So it is there. So everything, so I can make it smaller now. So they are all together. And I want the distance between this second one and the first one to be 3. So I choose the sketch. I take this one to this. I want it to be 3. 3. Then I want the distance between this one and this one. I want it to be 3. I want it to be 3 also. And then I want the horizontal dimension here to be 4 units. There's something wrong here. So, what is this distance? This is, I want to delete that. Okay, I want that to be 4 units. Then this in here, I want it to be 3. Let me just use my glasses here to see from the distance I have here. I want it to be 2.5. Undo. I want to take a dimension and push this one 2.5. So that one is already there, 2.5. And then I want this length here is not given. So that one is already there. Okay. So What about this one? This one should be 8. So dimension here, it should be 8. Okay, just choosing that dimension as scattered stuff. So why? So let me just go back. Control Z. So okay, so this is 3. So okay, so this one should be 8. And we can come, it's still 7 now, but we can come again and do the last one, which is we start from here, we go out, and then we come down here, and we close it here. So, and we put the dimensions of this one. So we put the dimensions here, we put the dimensions here and dimension here, and then we get, if I remove, from your sketch palette, you can remove all the dimensions and see what the thing looks like. And once you finish the drawing, you should have, everything should now come in black. So that is the best practice, is that everything should exist in black after you have specified all the correct dimensions and you have done your correct constraining. So after you have done all of that, you can move from that to something that looks like the step 1 here, which is this one. So that drawing will now look something like this with all those dimensions in there. And the black of all of this will show you the fact that all the constraints are already correctly done. Let us look straight at this by editing this sketch. If we edit this sketch, you can see that this is what you have on your slide. Let me see what the time is. It's already 5:02. This is what you have on your slide. And if you have your Fusion 360 close by, you can try and achieve this during the break if you want, and you can ask me questions about it later on. But if you remove the dimensions, this is what you have. If you can show the constraints on your palette, this is what you have. It shows that this is a horizontal line, this is 90 degrees, and so you can show either the dimensions or the constraints or both of them, or neither or neither. So all of this will give you this kind of drawing as half of the cross-section you are looking for. I want to stop here, and we'll continue from here after the break. You get a break of 15 minutes, then we'll continue.